Okay. Just checking, can the people online hear me clearly? Cool. And what about you? Right. Excellent. All right. So this, welcome. It's semester 1, 2021. And this is a revision seminar for Maths 1M. And I've had some requests about induction proofs and planes and points and lines in 3D and vectors and parametric curves and that sort of thing. So the rules for this seminar is it belongs to you. It is always okay to interrupt me, maybe wait till I finish the end of a sentence, but interrupt me and ask things and add any questions that you've got. I will stop every 5 or 10 minutes and just ask you if you've got questions. But it's okay to interrupt me. Please interrupt me if I have done something like written a minus sign in the wrong spot or not written a minus sign where it should have been. That's important. And I may forget things that are part of the course. So if you think of something that's an important point, please bring it up. Yeah. So, and anything I say may not cover everything that's comprehensively in the course. It's not my job, but I'll bring up things if you bring more things up. Sweet. And I will stop this at 11 because then I have another one at 11:30 for a different course. So yeah, just letting you know. I won't be offended if you leave either online or face-to-face. I know that people have places to be. Okay, so I'm going to start with induction proofs. And the first thing I'm going to do before I do anything is to say, how does induction feel? Like, how do you feel about it? Having people saying this.
I get the first part, the hypothesis, and the initial, and the last sentence saying that this is what was proved.
Hello, I'm so sorry I'm late.
It's all good.
But the middle part is sort of the actual doing.
So I'm just going to repeat that in case we didn't hear and just make sure I understand it. So you're okay with the beginning of what the hypothesis is and doing the first case. But then the middle bit of trying to make that bit of the proof work is you're just not sure. Yeah? Does everyone feel similar to that? Yeah. This is a common feeling about all kinds of proofs, not just induction proofs. Just had someone from Maths 1A ask me something similar about a different kind of proofs. And it is a continuing thing. And it's a difficult thing to even talk about, but I will actually make an attempt, okay? All right, cool. So I am going to talk about the general idea of mathematical induction, just to make sure we're all on the same page. So the first thing to know about mathematical induction is it's an axiom, meaning it's one of the assumptions that the whole number system is based on. You can't prove it from other things. It just has to be. So when mathematicians decided that they wanted to go back and figure out what numbers were really doing, and they had to create a list of axioms that they're built upon, list of rules that the numbers must behave this way so that we can figure out all the rest of the things that numbers do, one of the things they had to put in as a rule was mathematical induction. And it is the gold standard way of transferring information from one number to the next. That's what it's about. So the idea of, there is an alternative first rule, which is that, which goes that any set of whole numbers has a minimum. And you can prove mathematical induction from that. It doesn't feel like it at all, but that's another option, just in case you're wondering. Okay, so mathematical induction goes that like this. So here's the numbers. Going up, and they go like that. And you can start wherever you need to. And the way mathematical induction works is there's two pieces. you normally do the bit I'm about to describe second. So one piece is, let's hope that this is, yes. One piece is that, oh, of course that would be too easy. You can do it, right. One piece is that you create a machine. Damn it. There we go. Keep it out of the light. You create a machine that will say, if something is true here, then it will transfer that to the next one, and you conclude that the next one is true as well. And this is what you create when you do that bit of the proof that goes from n to n plus 1 or k to k plus 1 or however you do it. You create this thing that says if it's true at this spot, then it's true at the next one as well. And so that could be anywhere. If it's true at 3, it would be true at 4. If it's true at 4, it's true at 5. If it's true at 5, then it's true at 6. If it's true at 1, then it's true at 2. And no matter where you are, that thing, you can reuse that little proof machine to tell you that the next one's true as well. And the other thing you need for induction to work is for it to be true somewhere to begin with. So if it's the first time it's true is at 2, then the proof machine will make it true for 3, and that'll make it true for 4, and that'll make it true for 5, and it'll make it true for everything forever. And that's how induction works. That's the idea of it. Right. But you can have this machine, and it was perfectly good, but if it's not true at least one spot, then you're not going to be able to use it because it requires it to be true somewhere first. Okay. How do people feel about that? Yeah? Okay. But this is what it is in my head. Like, I'm going to actually draw that on the... There's a machine that transfers things to the next thing. So in my head, it really is a machine. It takes things in, it churns and bubbles, and it spits something out. And it takes in the statement that whatever the thing is true. Ah, damn it. True for n equals k, and it spits out for n equals k plus 1. That's what the machine does. That's this machine here. Okay. The reason I say this is really important that this is a machine that works on statements. It doesn't technically work on the number k per se. It works on this statement about the number n, or about the number k. And it produces a new statement at the end. And so that means that when you do this proof, it will hang off certain statements in certain places. You will have to say at somewhere, suppose that the thing is true when n is equal to k. And then there'll be some more statements that connect them together. At the end, it will say, therefore, it is also true for n equals k plus 1. There's no way of getting around that you have to say those things because it's a function that takes a machine that takes statements in and spits statements out. Okay. And all proofs are like that. If you want to prove anything, then you're required to say at the end the thing that you've proven so that people know that you're done. And you have to begin with the thing that you know is true that you're proving it from. Okay, that's just the general idea of mathematical induction. And people use several metaphors to talk about it, and they talk about dominoes or a monkey climbing a ladder or a game of whispers and blah, blah, blah. And they're fine, but I find this easier to process. So, yeah. Okay, all right. So it would be useful to have an example to try. Whoa. Does anyone have one that bothered them during the course?
Assignment question that I think most people got stuck on.
Yeah, but I was thinking that like the questions in induction probably won't be harder than the assignments that they gave. It was what was it? Written. I've actually got it right here. It was
Can I just borrow that piece of paper for a second? Oh, that one. Oh, yeah.
That one. I don't know if it's a good one to do because it seems difficult.
Could you do one that would be, yeah, like I said, more
I feel like it,
acceptable for an exam question?
Yeah, I mean, I have no idea what's acceptable for an exam question. I would not expect it to have too many things in it all at once, because this one had both trig identities and stuff. But it's not impossible. All right. Yeah, we can talk about that one in a minute if we want to. Okay. So I will say, I'll just make one up. There are several flavors of induction question that are really common when you just Google math induction problems. You'll find several different flavors, and then there's like a wild card, which could be about anything, like your assignment question. Let me just see. Yeah, that's great. Let's do that. This is the danger of okay. This is the danger of doing a revision seminar on requests that are given on the day. So you've got to. Okay. Yeah. What the hell? I'll read it out in a second. Okay. Prove that 1 plus 1 cubed plus 2 cubed plus all the way up to n cubed is the same as 1 plus 2 plus all the way up to n squared for all integers n greater than or equal to 1. So this one you'll notice involves a sum with an unknown number of pieces. That's a common kind of induction question. In Maths 1A, you'll learn sum notation, which will make it ever so slightly shorter to write some of these things, but it won't make it easier to understand. Okay. So with any proof, the first thing I want to think of is how this behaves. So I'm adding up the cubes of things, and it's the same answer as adding all the numbers up first and then squaring them. Okay. I can understand how that formula might work if I had. So this is all me thinking about stuff. It's not part of my actual solution yet, and I'm thinking that when n is 1, it's just 1 cubed, and it's supposed to be the same as 1. I'm going to do n equals 2 as well. 1 cubed plus 2 cubed, which is 1 plus 8, which is 9. And 1 plus 2 squared is also 9. So it works when n is 2. When n is 1, there's no pluses because there's only one thing. And so it comes out to the same thing. So it works at both of these cases. What I will say for induction is that it's not particularly useful to calculate it for each case separately, because that's not how induction works. Induction doesn't calculate separately that it's true for each one. You're creating a machine that will transfer it being true here to being true here. So what I really need to do is figure out how these things are related to each other. So with this one, I added on a 2 cubed. This one, I added a 2 inside the bracket and squared it. So I'm going to need to know how that does something. Let me try one more. So I already know what 1 cubed plus 2 cubed is. And then 3 cubed. So we'd have a 9 plus a 27, which is now a 36. And I can see that's a square number. And in this one, how would I get from 1 plus 2 squared to 1 plus 2 plus 3 then squared, because the 1 plus 2 squared is trapped, the 1 plus 2 is trapped inside the bracket with the 3. Seems to me the only way I could pull that 1 plus 2 squared out would be to expand this out. Like that. That was this squared plus this squared here and that squared here plus 2 of the two things multiplied together. That's how you expand out a square. And that would mean that this one is an answer I've already got. That's 9, because I already got that one. We're trying to figure out how to reuse the answers we have to figure out the other answers. Step did I do here? I noticed that there's a 1 plus 2 and a 3, and I kept them as separate things, and I had this squared, and 2 times this, and this squared, which is how you expand out a square. That's my guess. Like this is 9 plus 2 times 9 again, plus another 9. Oh, cool. So it's that 9 is a square number, and then when I pull that out, I'm left with 1 plus 2 plus 1, which is a 4, and 9 times 4 is 36. I'm just playing around with the numbers to get a fiddle of if could I do this without actually knowing what the one, yeah. It doesn't always help, but it's an idea to think, well, what operations could I do to keep this thing somewhere in my working? All right, doesn't always help, probably not going to help today, but I've got a thought that maybe part of this square number is going to come from something ending up being squared for all of these pieces. But I'm not 100% sure. Just going to have to give it a try. Okay. So that's cool. I've had a quick think about how I could transfer one to the other. I'm not too sure. Sometimes it helps. And so I'm going to do the proper proof now. So first, I've already done this bit. I know what happens when n is 1. So when n equals 1, 1 cubed is 1, and 1 squared is 1, and so therefore the statement is true for n equals 1. It has to start somewhere. Okay, we're not going to use this fact until later. In some very special induction proofs, you use the base case to help prove the other one, but that's very rare, so just point that out. Okay, suppose the statement is true for n equals k. Does your lecturer do like an n equals k sort of thing? Okay, good. Some of them just go for just n, but I like it to match this. Like this is when n is 1, and this is when n is something, but I don't know what the thing is, so I call it k. The point is that the k is a specific but unknown number. I'm not assuming it's true for all possible n. I'm just assuming it's true once at some point, which is called k. And that's why I use the word suppose instead of assume. It sounds a little less forceful. Suppose it's true. What would happen then? As opposed to assume it's true. Okay. And then I know that somewhere at the end, I'm going to declare that, I hope this is enough space, it probably isn't, but declare that the statement is true for n equals k plus 1. I know that this has to happen somewhere. And after I've made this machine, then I'll be able to say, since for n equals 1, it must be true for all n greater than or equal to 1 by induction. Something like that. I like putting the since it, combining them true together. So cool, I know what the proof looks like. This is the sort of thing if you have a written exam, even if you don't know what goes here, at least you've got the shape of the proof and you can get like a mark for knowing what induction is supposed to be like. Yeah. Okay. So supposing it's true for n equals k is supposing that this is true. Damn it. Like that. The thing I would like to conclude is the exact same thing, but with a k plus 1 in that spot and that spot. That's the difference between the thing I'm starting with and the thing I'm ending with. So in a technical sense, I'm supposed to finish with this statement. Like that. The reason I have included the k as well is because I know it's there. If I've already gone up to k and I want to go to k plus 1, it's an extra number on top of that. But this is the final statement I'm going to make, which is the statement I want to be true. How are we feeling? And sometimes people have said, but that's fairly stupid. You've just written down what it is you're wanting to do. Yeah, it's really important so that you know what you're going for. So now I can compare these two things to each other, and I notice that on this side what I've added is an extra k plus 1 cubed, and on this side I've added a k plus 1 inside the brackets. If I'm going to conclude something with an equals, my working is probably going to start at one of them and go equals, 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 and end at the other one. That's normally how equality proofs work. I just need to pick which one I'm going to start with. It probably doesn't matter, but one direction is usually easier than the other one. I find it easier to expand out. Like, it seems to me that if I started here and I wanted to get to there, I would have to factorize to be able to get things squared. And factorizing is harder than expanding. Because I don't have this big set of brackets with a squared on this side, so it seems that I should expand this out, which is what I was doing when I was doing it with just the numbers. So that's my guess. Expanding is easier than factorizing, so I'm going to start here. And I'm going to go equals, 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 and end with this. If I'm very lucky, I have enough space. So the other thing that is very important to know is that at some point you must use this statement. This has to be used somewhere. And because it's an equals, that usually means that either you're going to see this and sub that in instead, or you're going to see this and sub that in instead. So I need to keep this 1 plus 2 plus whatever squared. I need to make that appear so that this can go away. So I can replace it with this, because I have to use this. So I'm going to do what I did there. I'm going to just set it up 1 plus 2 plus k plus 1 squared. And so that will be 1 plus 2 plus k squared plus 2 times 1 plus times k plus 1 plus k plus 1 squared. I do not like it, Sam, I am. Okay, I feel like it's going to require us to know a very useful piece of information. Aha! All right, there was a hint that told us something useful. So I am going to just do what I've told, what I noticed, that this thing is here, which means I can replace it with this. That thing is here, which is equal to this, so I can sub that in. How do you feel about what just happened then? This 1 plus 2 plus whatever up to k squared is here. And according to my supposition, it's equal to that. So I can sub that in instead of that. And then this bit, I don't know. I'm going to need all of this to work out to k plus 1 cubed. Because I've already got the 1 plus 2 plus k cubed here, which is that bit. I'm going to need it to work, this last bit here to work out to k plus 1 cubed. That's what I'm going to need. So hopefully you notice at this point where I'm going, just a second, I'm going to compare where I am to where I'm aiming for so that I know what I'm going to try and achieve. So I have it, I don't know. This is annoying me. But there is a rule that the sum of the first k numbers is half of k times k plus 1. Just so you know. So this thing is equal to that. There's a formula for that that is apparently in the lecture notes. Yeah, it says, use this from lectures. Okay. Hopefully, if it's in something like this in the exam, they'll tell you that useful information. Okay. So this bit's good. And then the 2 times a half would be 1. And I've got k plus, so I've got k times k plus 1 squared and another k plus 1 squared. Oh, I'm nearly there. And I needed one extra line from what I had space for. So there's a k plus 1 squared in both of these pieces. And so I'll be left with k plus 1 squared. There's k of them here and there's 1 of them here. K lots of k squared plus 1 and 1 lot of k squared plus 1 is k plus 1 lots of k squared, k plus 1 squared. We're done. Because k plus 1 times k plus 1 squared is k plus 1 cubed. Phew. Okay. How do people feel about what happened there?
The orange text to be a bit of a stretch for me.
Unfortunately, sometimes there are prior bits of information you have to use. That particular one, it was probably also proved by induction.
Sounds about right.
You can prove it without induction if you're very creative. Yeah. And there's a picture version of this one actually, because you go 1 plus 2 plus 3 plus 4 plus whatever. And then if you have 2 of those, you can put the other one upside down just here. And now when you've got 2 lots of 1 plus 2 plus up to k, then you end up with a rectangle that's 1 higher than the k this way and k wide this way. And so the rectangle is k times k plus 1, but the actual thing you wanted is only half of that rectangle. That's a visual proof of this fact in orange. Yeah.
David, the marks come from the exam.
So there'd be 1 mark for knowing how, well, I don't know, but my guess would be there'd be 1 mark for knowing the structure of an induction proof. So for doing both this and this. And there would be 1 or 2 marks for, there'd be 1 mark for using this in this argument, and then be 1 mark for just not making any mistakes. That would be my guess for where the marks are coming from. Yeah.
You know when you took the second part of the equation, what do you make?
Oh, I took this part.
Yeah. Can you do the first part?
It could have been possible to do this bit and go forwards if we wanted. Let's try it. So I already made a move here that was an important move. If I just sub the k plus 1 into the original formula, it would have just said this. But I know that if I go to k plus 1, I would have had to get to k first. And so that was already a move that I made. That's a very useful move to make, is that if you've got a statement about k plus 1, find where the k is in that statement. All right, so according to my supposition, this is equal to that. So I could have replaced this with this. And then somehow I have to bring this k plus 1 inside that square. And that's tricky. But I'm going to need a k plus 1 squared if I do that. So what if I... All right. So the reason I've done that is I know if I'm going to factorize something into a square, I'm going to need the first bit squared and the second bit squared. When I expand out a square, like, you know, a plus b squared is a squared plus 2ab plus b squared. So if I'm going to factorize this k plus 1 into the square, I'm going to need it to be there. And this is somehow supposed to come out to 2 times k plus 1 times this. Yeah. And I'm going to have to do the step that I made earlier backwards, which is harder. I mean, you could. I mean, it's definitely got to have a k plus 1 in it. Like that. Because it's going to have to be 2 times this. So there's the k plus 1. And I guess I could put the 2 in. Because then I know it's got to have this, and then 2 times this times this. So this must be equal to 1 plus 2 plus whatever to k if it's going to work at all. So I'm just trying to set up what I would need. And then at this point, this would have to be whatever this is. And so you could just say, well, not knowing it's in the lectures at all, from lectures, 1 plus 2 plus whatever plus k is a half of k times k plus 1. And hope that it is in there. And so therefore, the original thing must be equal to 1 plus 2 plus k squared plus 2 times 1 plus 2 plus k times k plus 1 plus k plus 1 squared, which I can now factorize into 1 plus 2 plus k plus 1 all squared. Woohoo! Yep.
So in the exam, can we also write from lecture?
Yep.
You know?
I think so.
If they didn't tell us, but we remember from that,
That should be okay. Unless they specifically ask you to prove this fact, then you can't just say, well, it's true because lectures. You'd have to actually write a proof. And so possibly doing it in this direction would have told you that there must be an identity that says these have to be equal. If you were concentrating very hard about trying to make this as close as possible to something that could factorize, knowing that that's what you would have to do to get the final statement, you would have to factorize. Yeah. All right. Would you like me to do another induction to try and pull out some more morals for how to do inductions? Okay. Sorry? So this is one type, which is about things being equal, and they often involve sums. Another type is where you have to show that something is divisible by something. Oh man. I don't want to do the ones that are in the practice one. Give me a moment. Oh, yeah? Okay. We're going to prove that n cubed minus n plus 3 is divisible by 3 for n greater than or equal to 1. Well, integers. Okay. Okay. So I'm just going to think about it. N equals 1, I've got 1 cubed minus 1 plus 3, which comes out to 3, and that totally is divisible by 3, because it is 3, so that's nice, because 1 cubed minus 1 is 0. And when n equals 2, 2 cubed minus 2 plus 3 will be 8 minus 2 plus 3, which is 6 plus 3, which is 9, and that's divisible by 3. But I could tell even back here when it was just 6 plus 3 that it's divisible by 3 because both 6 and 3 are divisible by 3. Okay, so maybe what I need to do is figure out what this part here is and figure out that that bit's divisible by 3 because that will do a good job. Okay, and how could I jump from this to the next one? Like the plus 3's always going to be there, that's probably not an issue. I mean, this one's, well, of course they are, because this is 3. 3 is a bit of a stupid case. But how could I borrow from what happens back here? I mean, if I pulled out the 3, I don't know yet. It's not telling me anything, but I'm just trying to figure out how they're different to each other. The 3 is the same, so I'll focus on this. So that's what my working is going to do later. I'm going to run with that and see what happens. Okay. All right. So when n equals 1, 1 cubed minus 1 plus 3 is 3, which is divisible by 3. So the statement is true for n equals 1. It's a good start. That's my base. So they call it the base case. And now I'm going to suppose the statement is true for n equals some number k that is a specific number that I don't know what it is yet. And then I'll do some working and I'll conclude that the statement is true for n equals k plus 1, which will be on the next page, helpfully, which means I could fit some more in if I needed to. And so therefore, since true for n equals 1, also for all n greater than or equal to 1 by induction. Might as well put it in now. Okay. So the statement being true for n equals k would be that n cubed minus n plus 3 is divisible by 3. And this final statement is that So n plus 1 cubed minus n plus 1 plus 3 is divisible by 3. And somehow I need to connect them together. Okay. Yep. Oh, crap. Yes, supposed to be k. Thank you. See, well done for listening. I told you to do that sort of thing. Okay. So somehow I have to get from this statement to this statement. I do notice that if I expanded this out, I'd be able to get a k cubed out of this bit here. So that might be enough to help me from there. Yeah, not 100% sure, but it's worth a try. And I'm going to need to know how to tell if something's divisible by 3 as well. Because at any stage, when you write something you're not sure what to do, you ask yourself, what does this mean? What does it mean to be divisible by 3? It means it must be 3 times something. I shall call it M. Because that was the next letter I thought of. Okay, that's allowing me something that I can sub in at some point. So I'm going to start here, I reckon, and see what happens. K plus 1 cubed minus k plus 1 plus 3. And I can expand this and see what happens. That would be k cubed plus 3k squared plus 3k plus 1. Has anyone seen that expansion before? How about other people who are less brave? Okay. So you know, in case this is a useful thing to remember. But if you don't know it, you can always do k plus 1 squared and then times by k plus 1, and that'll work too. Okay. So, okay. I feel like this is a thing, you know, plus 1 minus k minus 1. Oh, interesting. So what I'm noticing is that this is already a multiple of 3, this bit here. It's got 3 times something. And this is a multiple of 3. And this is a multiple of 3. And this is the same as minus k. Aha! I can see the k cubed minus k plus 3 now. It's here. And so now I can sub this in. I'm just going to write it properly. So that it's easy to see what happened for the person reading it. So this thing is up here. I can replace that by 3m. And now I can pull the 3 out. Oh, not 3k, just k. And now I can finish. Because now I know that this thing back here is equal to that, and therefore, which is 3 times something, and so therefore it's divisible by 3. You okay? Figured it out? Okay. Oh, I probably just need to write better, really.
You haven't seen the lecturer's handwritten. Oh my god. If you're not thinking of the text,
Every year I joke that this is why I'm so good at teaching medical students. How people are feeling about this proof. What were the moves that made it possible to come up with this proof?
was something divisible by 3.
Yep. That was a very important move. Why was that so useful?
Oops, that's what we're trying to
Yeah.
prove.
Yeah, it's the definition, but it also meant that we're able to sub something in later, rather than just talk generally about being divisible by 3. So that's a good strategy. Yeah. So the other kind of proof that is common is, and there's wildcard ones, which are just about random things, and you just have to wing it and hope that you can see the thing that you're looking for in the thing that you've got. That's the general strategy. Other way around. See the thing that you already have in the thing that you're looking for. That's the other way around. This is the thing I was looking for, and I expanded it out until I could find the thing I already had. Yeah. Okay. So the other one is when there are inequalities involved. All right. Okay, this is an S. This is a squared. So there is no need for them to involve the letter N. They can use whatever letter you want. And that's a first message. And so this says S greater than 1. So that means the first case is going to be S equals 2. Three squared is 9. 2, the S is 2 is 4. And so 9 is indeed greater than 4. When S was 1, 3 to the 1 is also greater than 1 squared. So I don't know why they did S greater than 1, because it works for S greater than or equal to 1. Okay. So I can even do this because it's actually true there as well. So, but if they specifically said S greater than 1, then you would start at S equals 2, even if it's true when S is 1. It's even true when S is 0. Yay. Okay, sorry. 3 to the 0 is 1 and 0 squared is 0. Okay. So some of them don't start till later though. Okay. So I'm going to see what happens when S is 3. Well, the difference between between 3 squared and 3 is that it's times by 3, right? So that might be an important move in my proof later. And the difference between 2 squared and 3 squared, so that'd be like 2 plus 1 squared, which would be 2 squared plus 2 times 2 plus 1. I'm just trying to figure out how I would create this one out of the one before. So there's going to be either a multiplying or a factorizing by 3 going on this side, I reckon, in my proof. And there's going to be an expanding or factorizing a square on this side. That's my guess of what's going to be happening in my proof. Sorry? Because it's S squared, so the S is 3. And so just so that I don't get confused, there's a 3 to the 4, which would be the previous answer times 3. And there'd be a 4 squared, which would be the previous answer plus 1 squared. And so it'd be blah squared plus 2 times blah times 1 plus 1 squared. That's my guess at what's going to happen. Not sure, but I'm pretty sure we're going to have that because the move from 3 square cubed to 3 to the 4 is timesing by 3, I'm going to have to either multiply by 3 or divide by 3 or factorize a 3 in my working. And expanding squares is going to be useful too. So that's my thinking. All right. So when s equals 1, 3 to the power of 1 is 3, and 1 squared is 1, and 3 is greater than 1, and so therefore 3 to the 1 is greater than 1 squared. So the statement is true for n equals 1. S equals 1, damn it. All right. Suppose the statement is true for s equals k. And then sometime later, I'm going to conclude that it's true for s equals k plus 1 as well. Since true for s, damn it, s equals 1. And your little dog too. Sorry, just the laugh was very cackly. Since true for s is 1, it must be true for all s greater than or equal to 1 by induction. Okay. That's the classic ending. So here we have, for s equals k, that would mean that 3 to the power of k is greater than k squared. Oh, I'm so glad I'm not using s's anymore. And we would like to conclude at the end, therefore 3 to the k plus 1 is greater than k plus 1 squared. So I know that the move from 3 to the power of k to 3 to the power of k plus 1 is multiplying by 3. So that's what I'm going to use. So I'm going to start here. I'm going to say consider is a nice thing to start if you want, to make it sound like you've started something. So this is equal to 3 lots of 3 to the power of k, because that's how you go up 1 power. And now I can sub this in. Because 3 to the power of k is greater than k squared. Not everyone's comfortable with this kind of working, so I'm just going to check how you feel about what I just did. Yeah? Any thoughts or questions about that?
Why is that inequality? Why is it not?
Because what I subbed in was an inequality. So this is saying that 3 to the k is more than k squared. So anytime I see something involving a 3 to the k, then it'll be more than the thing involving k squared as well. Yeah. So if you really want to convince yourself, you can go 3 to the k is greater than k squared, and you multiply both sides by 3, and you get that. If you really want to believe it. Okay. And somehow this has to get to be either equal or greater than k plus 1 squared. I do not like it, Sam, I am. I'm going to have to factorize something, right? I'm going to need a k squared and a 2k and a 1 to get to this. All right, well, let me just say that this thing is equal to, so each symbol just refers to the one above it. So this thing is equal to a k squared and a 2k squared. And the reason I've done that is that this thing at the end is k squared plus 2k plus 1. So if I can make the k squared, I have a chance of getting where I want to go. But just be careful, this equals is only referring to the thing directly above it. Okay. So if I could be sure that this was greater than 2k plus 1, I'd be good. Damn it, that's a whole separate proof. Now I know why they did it as s greater than 1. Can I go back and change it? Alrighty. Changing my original problem to be 2. And I'll tell you why I thought that. Okay. I'm going to separate this one more time. I didn't like the 2k squared because I needed to just be 2k. I wanted something with just a k in it. And so I'm going to separate it one more time and get k squared plus another k squared plus another k squared. Okay. Are you ready? It's not going to be equals. K squared. I know it will be equals, just a second. One more thing. I need this to be 2k, right? So I can factorize. So it is something times k, it's k times k. But we assume that all the s's, including the k, are greater than or equal to 2. So this is greater than or equal to k squared plus 2k. Because that k is greater than or equal to 2. And we have one more move. You ready? It's a fun move. K squared is at least 4 because k is greater than or equal to 2. And so this is definitely greater than k squared plus 2k plus 1. So this is since k is greater than or equal to 2, and this is since k is greater than 1. And this is equal to k plus 1 squared. Wow! I made a lot of moves there. Inequality reasoning is really interesting because you're always, if you're making things greater, you can always replace something with something that's smaller than it, and that's okay. How are people feeling about what happened there? This one might have been easier backwards. There. So in my head, just so they know, what I was thinking at this time was that k plus 1 squared is k squared plus 2k plus 1. That's what I was thinking this whole time. So technically I was working backwards from the other end, but I wasn't writing it down. And so when I saw this, I thought I really would prefer it to be k squared plus something times k plus k squared. All right, and so I did that because then it's just something times, that's k times k. And then I know all the way back here that this thing starts at s equals 2, which means my k has to be greater than or equal to 2, because that's where it started. So when I'm here, since k is greater than or equal to 2, this must be greater than or equal to the same thing with a 2 instead of a k. Yeah, that's the move. How do you feel about that in the Zoom? I'm sure there's other ways of doing this one. This is just what I thought of. Sorry? Yeah, inequalities allow you to use that sort of move. And I use a similar move here. K squared is definitely more than 1. And so I can say that this thing here is definitely more than this thing here. There are some technical details, like if you've got a minus times it and you replace it with something that's bigger, it's the wrong way around and stuff. But as long as there's positive numbers, it'll all be okay. And the final step is that 3 to the k plus 1 was equal to this, and this was more than this, and this was equal to this, and this was equal to this, and was equal to this, and this was greater than or equal to this, and this was greater than this, and this is equal to this. So if you follow that chain through, you get that 3 to the k plus 1 is actually greater than this final thing, because somewhere in the middle there was a greater than. In my head, there's actually, if I actually follow this through, I can have 3 to the k. I've got a number line vertically. Here's 3 to the k, and I know it's equal to 3 to the times 3 to the k, and it's more than 3k squared, and that's equal to k squared plus k squared plus k squared, and that's more than k, that's equal to k squared plus k times k plus k squared, and that's more than k squared plus 2k plus k squared, and that's more than k squared plus 2k plus 1, and so therefore this is more than that. Each step moved down a bit, and sometimes I stayed at the same level. Yeah. All right. So since I also have this one that k is greater than or equal to 2, I can make this move here. Yeah. All right. Always come to Maths Learning Centre to talk more about it. Yeah. I personally won't be there tomorrow because I'll be in revision seminars all day, but I will be in the Zoom on Friday, and I'll be there next week. In case it's relevant that your exam is, I'm not allowed to tell you when your exam is, because then it would be my fault if I told you the wrong day. It's university policy. But so I will be there on most of Monday. Okay. Has anyone got an overall strategy that they're going to try and apply?
Do the Mobius first. Because most of those you can sort of.
Oh, I meant for induction.
Oh, yes. So, exam.
No. We'll get to the overall exam strategy later. So I would recommend knowing where you're headed, like that thing where you separate the two pieces so you can compare where you're going to where you are, and always looking for ways to find the bit you've got in the bit that you're heading for. And that sounds really vague when you say it, but we've done it 3 times now. So yeah, I think I'm going to draw a line under induction and talk about some other things. Got half an hour. If you had a preference, someone in the Zoom's already expressed a preference for talking about parametric things over planes and stuff. How do people here feel? Sorry? Okay. This is going to require me to check off against you to what you've seen in your course. But I will talk a little bit about just general vector stuff as well. Okay. I don't really know. I'm just going to talk around it and see where I end up. Pardon me. It's a bad title, but that's where we are. Parametric curves and vectors and stuff. Okay. The first thing I'm going to say is a general thing that I always say when I talk about these things, which is that in coordinate geometry, which is what you're doing, where you're describing what's happening to things in space or on a plane with coordinates, there are two ways to describe an object. So you have points which have coordinates, which may have that in 3D or that in 2D. And those coordinates tell you how to locate a point at a time. And then we have vectors which have the same coordinates, which also have coordinates. You do vectors with coordinates as well. I mean, I think they call them components. And so they look the same. And it's actually extremely useful that they look the same, because the arithmetic that you do on the vectors is the same as what you do on the points. And the difference between them is that vectors are thought of as journeys between points. But vectors are not thought to be different if they are connecting different points. And so this vector is thought to be the same as this vector. Whereas these points are all different to each other, but the vectors are thought to be the same if they have the same journey. And technically, you could draw them not as straight arrows. It doesn't really matter that it's a straight line. It only matters that you get from one place to another. Yeah. This is not really all that different from the way numbers work. Ordinary numbers are already, these are locations, right? Ordinary numbers are already both locations and journeys. So with ordinary numbers, just as an aside, for numbers, you've got a number line, and when you do like 3 plus 2, you go 3 is a location and plus 2 is a journey. And then the new location is where you end up. And so you've already seen things being both journeys and numbers when you first learned about how to add things that were bigger than 10. And you go, okay, 9 plus 2 is 9, 9 plus 10, 9, 10, 11. And counting on, which was one of your first strategies for addition, was treating one number as a place and the other number as a journey. So mathematicians don't really see points as different things from vectors most of the time when they're writing the calculations. They're just, this set of coordinates sometimes represents a location and sometimes represents a journey. The calculation is the same either way. Okay, but in my head, what happens is, and I will fit it on here, that point plus journey equals new point. Okay. So if you've got A and B, and this is the vector from A to B, then A plus the vector AB is the new vector B. Okay, just something I wanted to say, because I just have to remind myself of this every so often. Okay, how do people feel about that? All right, so this is an extremely useful thing for creating a parametric version of a line. But before I do that, sets of points. So a line is a set of points. When you draw a line in 2D or in 3D, there's points that are part of the line and there's points that aren't part of the line. This set of points, that's what the line is. And a curve is a set of points as well. Okay. And sets don't have to look like lines like this. They can also be, you know, the inside of a circle, for example. That's a set of points. And what a set of points has is a rule for deciding whether you're part of it or not. So one rule could be, look, there's the drawing. It's in the set if it's in the drawing, and if it's not, if it's not. But most things have two separate rules for deciding whether you're in the set or not. And so a line, for example, like this, could be drawn as either an equation, so that's one equation that tells you whether you're on the line. There's more than one way of doing this equation, but this is the easiest way I know. So this equation is telling me is how to tell if a point is on the line. If I get a random point and I want to say, is it on this line? I could sub it into the equation and see if it comes out to 1. And if it did, it's on the line. And if it doesn't, it's not on the line. So that's one way. The other way to tell someone where the line is to tell them every point that's on the line. So I could, for example, say that this is an intermediate stage, that y is equal to 3 minus 3/4 of x. For example, that's the slope-intercept form, because it goes through 3 and the slope is minus 3/4. And what this is telling me is how to calculate the y-coordinate from the x-coordinate. And that's saying that the points on this line are x, 3 minus 3/4 of x. And to create all the points on this line, all I need to do is pick as many x's as I want. I could just keep picking x's and do this calculation, and it would produce a new point on the line. If x is 1, I'll get 1 minus 1 and just let me unplug it again. Just a second. All right, we're back. Okay, so this is telling me how to make points on the line. I keep picking x's, calculate the point, there's a new point on the line. I can make as many points on the line as I want using that system. So this is called a Cartesian equation. This is a parametric form. And the parametric is referring to a parameter, which is a changing variable that tells you which point you've got. How are people feeling? Okay, good. Traditionally, you put a T in this spot when you do parametric form, but whatever. You're allowed to use whatever letter you want. Okay. So every set has, almost always has both versions. There will be a Cartesian form, which tells you how to, an equation that you can sub things into to decide if they're part of the set, and a parametric form that will allow you to figure out what every point in, new points in the set by just picking new values of the parameter, which would be usually T. Okay, and lines have two of these. There is also a vector version of this if you want it. All right. So I'm going to draw this same line and think about it in a different way. The vector form is, in essence, still a parametric form. It still tells you how to locate every point on the line. So vector forms are in this camp. They're how to locate every point. So I could locate every point on this line in a different way. I could think of it the way I was thinking of this, where I went a point plus a journey is a new point. So I could say, what if I wanted to locate every point on this line as the new point in that situation? So I could say the point on the line is the new point. I could start, for example, at 0, 3 and add on a journey to get to the point I'm thinking of. And that journey will have to be in one of these two directions. So for example, to get this point, I could add on the journey plus 4 for x and minus 3 for the y. For example, and this would be start here, do this journey, and plug your computer in. And arrive at this point here. Okay. But what if I made my journey longer or shorter than this distance, I would get to other. You can do it. Right. So if I went only halfway, I would end up here. If I went half of this journey, I'd end up in that spot. If I went twice that journey, I would end up in this spot. If I went -1 of that journey, I would end up in this spot. So I could go some multiple of that journey and end up in all the other spots on this line. And that's that is a vector form of this line. But I could just as easily have had started here and gone multiples of that journey instead. Or at any of the points and any multiple of whatever journey fits on the line. And that would all work as a vector form of the line. All right. Someone was asking what's that look like in 3D. This is a line in 3D. At this point, I can get to any other point by adding on this journey. That's a journey. There. So from at this point, I can get to that point by adding on 1 of that journey, this point by adding on 2, this point by adding on 3, this point by subtracting 1 of the journey, and so I can create this line in 3D in exactly the same way as I create a line in 2D. Right. So this vector form is the easiest way to make a line in 3D. In 3D, lines don't have equations like this. you need two equations to tell you which points are on a line in 3D. Not, yeah, to be able to decide whether a point is on a line. So a line has two Cartesian equations when there's two equal signs in that. Okay. Planes are similar. You can do planes with Cartesian forms and parametric forms as well in 3D. But a plane, with a line, there's only one direction to go, or two technically, forwards and backwards. But with a plane, there's two directions to go to figure out where you are on the plane. So if I had a solid plane, such as this, I'm very clever. I can fit this under the thing. I have a plane in 3D, like, need more, like this. Then you can locate a point on it and pick two vectors and go, oh, well, I could go 2 of this and get at that point, 2 of this and 1 of the orange one and get to this point, minus 1 of this and minus 1 of the orange one and get to that point. I could use 2 vectors to get to every point in this plane. And because it's a plane that has 2 directions, I need to have 2 parameters to tell me where the plane is. I don't know if you did parametric version of planes in this course, but you do need them. But you only need one equation to make a plane in 3D. So planes in 3D will have an equation like, and maybe I need to put my document camera back in the right spot. Something like that. And this will be an equation that will tell you how to decide if a point is on the plane. But it also has a parametric version, which is easier with a vector. You know, maybe we've got something that goes through the point 0, 1, 1, and then these 2 directions are whatever they are. And then we could say that all the points on the plane are plus something times minus 2, 3, 6, plus something times 5, 1, 7, for example. That's just an example. This is not that plane. I really could have been better about that. Yeah. And this is you know, how to get to every point. So I believe in this course, if they say find the equation of the plane, they mean this. Yeah. Because this technically isn't an equation, it's a description of each point. Yeah. Okay. So a parametric curve, the fact that it says parametric, means it is a description of every point on the curve. A new value of the parameter will tell you a new point on the curve. But before I move on from that, thoughts or questions about what I've said so far? Okay. A curve can be made parametrically with one parameter. Plane needs 2 parameters, and a plane is a flat thing, and you can have curved surfaces as well, and they're made with 2 parameters. A curve is like a line. It only takes 1 parameter to tell you where you are. But the way it's described is it's a description of every point. Okay, and so for example, you might have a curve in 2D like that, for example. T squared, T minus 5. I have no idea what that looks like. Desmos is actually good for showing you what these things look like. Ta-da! And I could choose my t to be like from -10 to 10, and it would give me more of the curve. So Desmos just makes a good guess if you put a t in a formula that it's a parametric curve. That's nice. Okay, so it's worth noting that if I choose different zones for where the t is, I get different results for what points I get. Each value of t produces a point on the curve. And that's that point there. And if I chose a different value of t, I would get a different point. And that's this point here. And that's the idea of a parametric description of a curve. Each value of t gives you a new point on the curve. And if you want all the points on the curve, you use all the values of t and it produces the graph. And this can just as easily be done in 3D as it can in 2D. I'll show you one in a minute, but we'll get there. So you have to tell someone what values of t you're using. And you're allowed to use all values of t if you want. But you could also use like cos theta, sine theta for 0 is less than or equal to theta is less than 2 pi. That's a parametric curve as well. That's a circle. Of radius 1. Cool. There's nothing really more to it than that. I mean, in the same way as ordinary equations, you're supposed to be able to forge a connection between like y equals x squared and the shape that you expect it to be. There are some really common, well, basically this is the common parametric curve, or a straight line, basically. And they're the two you're supposed to be able to recognize. Straight line you can tell by separating it out into the vector form, and then you go, oh, it's a straight line. This one, that'll do it. Okay, so there is slightly more to it, because now that we have a value, a parameter, you can imagine what happens as the t gets changed. So if I start with a value of t equals 1 and I move forwards from there, then that will move the point on my curve. Not that one. So as I change the value of the parameter, it moves the point on the curve. And so I can imagine, well, if t was, say, time, then what would that mean about the speed that this point is moving? And what would it mean about the direction that this point is going? Can I just check? Someone in the chat was asking about, is this the sort of thing you were asking about? Diane? Mainly in between a range, yeah. Okay. Okay. So I'm just going to check your original question. All right. So Finding the distance travelled from t equals 1 to t equals 5. Sweet. So that is hard to find the distance travelled along a curve. I have a feeling that there might have been an assignment question or a practice question about that. Okay, what did it say? Does anyone have it? It would be involving integrals. Okay. So what I will say though, is I can at least do derivatives. If I'm somewhere on a curve, and I know that there's a value of t, that I choose these values of t, like between 0 and 1, for example. And as t is a particular spot, and as it's moving forward, this point moves along this curve. And if t moves forward a little bit here, the point will move forward on the curve as well. That's what I'm imagining. Depending on the way your curve is set up, sometimes if this moves forward at a steady rate, this will go faster in some places than it does in others. And you're interested in that speed that it's going. And I don't know, I'm just going to tell you what I know, because I don't know what's in the official things in your course. But I do know that if you've got something like, say, this curve here, I shall call this point, I don't know how your lecturer does this. Yes, awesome. Yeah.
This is tutorial 7, so it's pretty nice.
That's okay. Sweet. Okay. Why call it v? Oh, that is the velocity. Okay. Okay, so the position I'm just going to call x, if that's okay. I don't know, x with an underline under it because it's in bold. So I'm going to do this example here, and that actually looks like not like that at all. I'm going to start a new page. Something like that. Okay, and I know what that looks like because Desmos told me, something like that. And I might be interested in what speed it's going at a particular point. So the thing is that the velocity is technically a vector because as it moves forward, it's going at a particular speed and a direction as well. And so that speed will be the derivative with respect to x and the derivative with respect to y. Right, awesome. Let's do that one. Okay.
Wouldn't that make like the original
Yeah, so you're assuming that t is in seconds and that the grid is in whatever the grid is in. So if the grid is in meters, then it would be meters per second. If the grid is in centimeters, it would be centimeters per second. If the t was in hours, it would be centimeters per hour. So it doesn't really matter. Whatever the units are that it's measured in, that's what the units are for the derivative. Is that what you're asking?
No, I'm saying you said the definition of divisible, right?
Yeah.
But that means you must have started with displacement.
Yes. But what I'm starting with is position, which is, so the position that I'm at is this, which can be thought of as a displacement from the origin. No, it's just the spot that you're at, which is what displacement is. It's the spot that you're at. How far you are from the beginning as opposed to how far you traveled to get to that point, which is a different thing. Yeah. So the velocity would be the derivative of this. I'm just going to do mine. So that would be 2t1. So that's saying that if I'm at position t, then if I draw this vector as an arrow from where I am, it will point in the direction that the curve is currently going. It'll be tangent to the curve, and it'll be and the length will be representing how fast I'm going. And so this is going faster the further along the curve I am, because this 2t gets bigger and bigger as time goes on. Okay, so this is the literal vector velocity. So for example, at t equals 3, the velocity at time equals 3 is 2 times 3, 1, which is 6, 1, that vector. And so that's what that's telling me is that at t equals, so I'm just going to do the position as well. This is the position. That's 9 minus 2. I shouldn't have done t equals 3. Just going to make it bigger. It doesn't really matter. I do not like it. It shouldn't be negative. Maybe we're still... So it doesn't match the graph I drew in Desmos, so I'm just slightly confused. So this is telling me I'm at this point, minus 2, and if I go 6 this way and 1 this way, that's the speed it's going at. So basically, if time moves forward just a little bit, then the curve will go a little bit of this distance. That's the idea. And so I expect the curve to be generally going upwards at this spot. Just give me a moment. Oh, that's because I drew t minus 1, not t minus 5 in my original graph. Okay, the world makes sense again. Let me just... not that one. That one. So here I am at s equals 3, and I'm at 9 minus 2. And if I move forward just a little, I will go in the direction of the vector 6, 1. So I'm going across 6 and up 1. That slope there is about the same as the graph. In fact, if I zoom right in on this until it looks straight, then the slope of this is 6 across and 1 up, which is what that vector 6, 1 is saying. Yeah. Okay, so that's the vector velocity. The speed at that point is the length of this vector. Yeah. I'm just checking what questions we'd be asking. So this is the velocity. And the speed at t equals 3 is the length of the velocity vector. Do they use a double bar? Yeah. Which is the length of 6, 1, which would be the square root of 6 squared plus 1 squared, which is root 37, which is 6 and a bit. That's That's what calculators are for. .08, 6 and a very small bit. So that's how fast it's going. It's going at, if the x coordinates and y coordinates were in meters and the t's were in seconds, it would be going at 6.08 meters per second. Yep. But I mean, a second later, it will be going at a different speed. And the acceleration would be the derivative of the velocity, which would be 2, 0. So it's always accelerating the same. The speed is increasing at 2 meters per second in the x direction, and the speed in the y direction isn't changing. It's always going up at the same rate. Yeah. Right, and the final question, and I know I'm supposed to finish at 11, but I just want to do the one that actually people ask me. The final question would be the length of the curve from one place to another. All right, here we go. This I will have to look up. I don't do this one very often. I can make a guess. From t equals 0 to t equals 3. Okay. So it was down here, right, wasn't it? Like that. We're going to know how long that curve is. So in essence, how much graphite came off of my pencil onto the page, really. I could do it as a volume if I wanted. That's what I need to do. So it's got a little longer than this distance. That's the literal as the crow flies distance from this point to this point. But if you want the arc length, is that what they call it? The arc length is this distance, which is a little bit longer. So if you didn't have time, you could find this distance literally as, you know, Pythagoras' theorem, and say the arc length is longer than that. If you couldn't remember it, then at least you'd say something that was useful. And you would get, oh, you know, if it made the difference between passing and failing, they would give you the mark.
From lectures.
Yeah, from lectures. But the actual thing is that what you're going to do as the point moves along, as t moves forwards, you accumulate arc length. You just keep, it's a running total of how much arc length you've covered so far. And running totals is exactly what integrals are for. That's what integrals do. They do running totals of stuff. And so I need the running total for any point, and I particularly need it for the running total when I'm up to 3 so far. And so I'm going to definitely be doing an integral from t equals 0 up to t equals 3, and then dt. I have to figure out what goes in this spot. I know that when t moves forward an eensy-weensy bit, if I'm zooming in on this here, that's my magnifying glass. When t moves forward, if here I am at a particular value of t, when t moves forward an eensy-weensy bit, the distance that this moves forward will be the velocity times the time. So distance equals speed times time. So if I move forward a tiny piece of time, that's what dt is, and the speed will be the length of the velocity vector. So this is what I'm going to put here. There we go, I was able to figure it out. There you go. Cool. That's how you do it. The velocity, the amount of distance we're accumulating is a speed times a time, because that's what distance is. And this is the speed, and that's the time I move forward, because I only move forward a little bit because I'm doing a running total one tiny piece at a time. Okay, so the length of V was the length of 2t plus 1, which is the square root of 2t squared plus 1. Sorry, plus 1 squared. which is absolutely awful. I do not envy anyone attempting to do this integral. Just going to look at this example that was here. The one in the course notes, they specifically chose one that you know how to integrate. But the length will now be the integral from t equals 0 up to t equals 3 of the square root of 4t squared plus 1 dt. And that is not an integral that you've been taught how to do in this course. That's in Maths 1A, that one. If there was a t out here, I could use substitution. But there is not. So, sorry guys. A lot of past exams have said, set up the integral but don't do it in Maths 1M. They said, write down the integral that would calculate the arc length, but do not calculate the arc length. Yeah, so we will stop here, and that's what it is. Or they will separately tell you what the integral of a function is, and it will just happen to turn out to be the function that you had. Any thoughts or questions about that now? Good. That idea of a moving point is, yeah, it helps. Oh, I was going to show one more thing, which is you can make curves in 3D. Which is what the change is for. There's nothing stopping you having a curve. You know, for example, this curve, which goes around my leg, a spiral, and there would be some sort of formula that would tell you, given t, what position you are on the spiral. That's a curve. But it could be just as easily in space. You know, that sort of thing is a curve in space. It looks like it's in a plane, but it's living in space. And you can have things that require all the space that you're in because they go round and round and up and down. Yeah, so, and these velocity things, they all work just exactly the same in 3D. It's just that you have 3 coordinates to differentiate instead of just 2. Yeah. So there you go. I don't know if you did 3D curves. Did you? Oh, there you go. Works the same. The point is that it's a single vector. Straight lines are parametric curves if you write them in vector form. They are curves. They're just the least curved curves. So for a mathematician, they need one word to describe all of those things, and they call them curves because most of them are curved.
Yeah, but it contradicts with everything that you read on what a curve is, a straight line.
If you learn anything in any discipline at university, they will redefine old words to mean new things. If you learn biology, they will redefine what a leaf is, and your mind will be blown, and it will be not what you thought a leaf was. And they'll redefine in biology what a berry is, and you go, oh my goodness, watermelons are berries, but raspberries aren't. Like, what? So that's just science and maths generally, and history and all those things. They take ordinary existing English words and they give them new meanings, or whatever language it's in. And so we have decided that there's no point having a new word just for straight lines because they behave the same way as everything else does. So I'm just going to call them curves. That's just what they've decided. But yes, you're right, they're not curved.
They eventually will be.
Sorry?
But they eventually will be. There's a straight line will always eventually be clear from the universe.
But the universe that the straight lines are living in the maths is not curved.
The universe is sort of like circular on you.
Yeah. But curvature, but there's, paradoxically, they still have a word for curvature, and a straight line has zero curvature. Yeah, but that's the thing, right? You define a quantity called curvature, and the quantity is allowed to be zero. And so it still has curvature, it's just that the answer for that curvature is zero. Sorry? Oh, that's all right. That's just, zero is still a number of cookies. You do, but it's still a number of cookies. Correct. There is no way to resolve this. Like, it's impossible. I'm going to stop the recording there. Thank you very much.